Hey folks, thank you all for joining today. I'm Athish and I have with me my colleague Samiran Roy. We are both part of data science team at CRED. Today we'll be talking about generative AI agents. How do we go beyond LLMs and sort of go deeper into what next can we do? This is the outline that will be going on today. The aim is that we go into the depth of each of these components. So here you see a definition of LLM agent. Why is the buzz that is going on with LLMs giving us a spark of what it means to have reasoning capabilities, to have areas, ways in which you can reduce your problem into subtasks, you can understand, you can have natural conversation within bot. And those sort of capabilities is what help us think more about LLM agents. And this has enabled us to do sort of a lot of things that was not imaginable some time back. Just take a look at this example. Let's say if you are planning a trip to Japan and you give this to an LLM, what it will tell you is that it will give you a very generic output, that you should care about your visa documents, you should care about your budget, these are some places that can give you, and so on and so forth. Now let's say you're a travel company and you have a lot of documents on past trips, what the requirements with the users was and what you had given as a trip itinerary to them. And now you use all this information with RAG, and you basically have a much powered LLM, and it will give you a lot more better information suitable for the user, and that will help you get better at it. Now assume you have an LLM agent. What the conversation will look like. Now, first of all, it will ask, let's say you give it a very high level item that want to plan an itinerary to Japan. What it will do is it will first break down it into multiple steps, sub items that you need to process, and then it will ask you clarifying question. Let's say, do you want it as an adventure trip? Do you want it as a romantic trip or business trip? And then sort of changes output based on that. And then it will go ahead and again do a lot of things for you, not just itinerary planning, but it will look, let's say, the flight details, it will go to hotel reservation, it will reserve for you, it will attend to your calendar and attach all the itinerary, do all the bookings, and boom, you are done end to end. Sounds a lot like feeling like Iron Man with Jarvis, and too good to be true, but trust me, it's not going to be so far away in the future, and very soon you will have a capabilities similar to this. And just to showcase why are we seeing this spark, I'll give some examples about some of the demos that we have seen very recently, which sort of give us this promising areas where we can basically see these at least in action. Now, this is an example of a paper, Mind to Web. What they did is they basically understand the interaction users have with day-to-day sites based on the top sites that we have, and it trained a LLM on top of it. Now this LLM, what it can do, let's say you want to book a flight from India to London, and you want to go on, let's say 20 April, come on 24th April, it will enter every detail for you, and it will come back with the final itinerary, even pay for you. Let's say you want to go on Twitter, you want to, let's say, find someone, follow them, like the latest tweet and all that, it can do all those action automatically without a human intervention. This is another paper that was recently released by Tencent. This is app agent. What it does, it learns based on how you interact with an app, similar to what Mind to Web did for web. It does for your apps. So let's say what you're seeing is a final inference phase where, let's say, you just give a quote, beautify the photo for me. You can make it a little more complex, let's say increase the light or something, and it will automatically do all those actions, and then you have final your Instagram filter already applied for you with just a text phase. You don't even need to touch the phone. This was another paper which caused a lot of news, MetaGPT, because what it claims is you just give a one-line text as an input that this is you want. Let's say you want a shopping website, you want, let's say, a simulation game of snakes and ladders or something similar, and it will generate a lot of details for you. It will act as a product manager, write a outline for you. It will act as a project manager, decides on what all steps needs to be done. It will act as a tech lead and architect and give you all the important details how the API should look like, what data structure should look like, and basically in the end you have an engine agent which basically does the coding for you. So in the end, just with a single input, you're getting codes along with the final SOPs and everything, And this is how it looks like. You have different product managers, architects. So these are different agents, and if you look at different demos on the website that they have, you will see that how it essentially encapsulates a lot of details from you and enables you to use LLM up to a max of their capacity and a lot of increase their capacity that they already have. Now that we have looked at a lot of these examples, let's also understand now how has this evolved over time. Now we are at LLM agents, but how it started, what are the thoughts that you had. So agent, the initialization sort of happened in philosophy where they believed agents to be entities which has intention, which has beliefs, personas, and also abilities and skills to do action autonomously. And that was when translated to computer science, it becomes that we wanted computer to enable computers to do tasks automatically, understand user interest, understand user intention, and do those tasks for them. It started with, in 1950, we had symbolic agents where we use symbols, we use simple rules to have different AI agents. Like mycene is one where we used to detect bacterial infections. You have another logic theorist which was basically used to prove a lot of different theorems. They had similar like that. And then we moved on to reactive agents, which does not care about long-term planning. All it cares about is the current situation. It takes that into account and try to adjust accordingly whatever it wants to do. Now think of it like your thermostat or your Roomba vacuum cleaner. Where is it right now? This is the next step. I just want to focus on this. I have no idea about the next steps that I have. Then came reinforcement learning based agents, which are essentially given an end output that you have. Let's say this is the target, you have to win a game of chess, you have to do this. That was the end target. And based on the end target, when you train, you give it rewards. That if you're moving in the right direction, you get positive rewards, else you get negative rewards. And based on that, this is how it learns. So it has a long-term perspective into picture, and it keeps on training based on that. A good example would be AlphaGo or OpenAI Dota 2 bot. And then came transfer learning and meta learning concepts, which basically means that you are learning on an area where you have a lot of context. You understand a lot about, you have a lot of data about some particular area. Let's say you just have conversation for you to train on, and then you train some auxiliary task on that and use that to transfer learn where you are not very clear on, and basically you have very little data to train on. So it should be a similar task, so where you can do transfer learning, and it basically learns whatever it is learned from here and apply it here in a very small amount of data. And with meta learning, the idea was that you basically learn how to learn and then implement it in a different, basically very different scenario. ULM fit is one of the example that was the initial ones in transfer learnings. And now finally we have LLM agents. And what they do is they use GPT or Llama 2 models or any LLM model as their base reasoning engine. And they have sort of these capabilities that they can connect with data sets, they can have understanding on what needs to be done, and then basically abilities to do all those tasks. And we basically combine them with a lot of different capabilities like memory. We give them memory, we give them different areas to understand on past context, future context, and all those things. So those are the agents, and we'll go deep down into what it corresponds to, what are the different components which enable these things. Mind2Web that we just saw, there's another tool former that is there, which from a survey that basically looked at the number of papers we had for LLMs, agents. And if you see in 2021, you just had one or two paper, and now we have more than 150 papers coming out by August 2023. So in 2 years, the rise has been exponential. I would say it's a very nascent stage still, but the number of people getting excited about this is increasing, and you can have either specific agents, which are like tool agents, or which just learn to use the tools. Or you have web agents, which like we saw Mind2Web, or you have game agents, which are specializing in the game areas. So now that we understand what are these, just a way to decompose it into what are agents, what it does. So it essentially empowers LLMs to go beyond just the text producing output and sort of interacts with other areas. You can interact with different databases, you can attend to different APIs, or you can create a lot of different context from this. And the way to do that is, what's unique about agents is that they don't just have a fixed chain. So let's say some of you have used LangChain, you can define a fixed chain that you do this, then you do this, and you do this. Okay, that's a fixed chain. What agents are able to do is move from fixed chains to a very dynamic chain. You don't know what those tasks are beforehand until you've got a set of tasks that you created for yourself. So let's say if your end goal is, let's say, browse something, you don't know where you'll start or where you will end. So you have to use a very dynamic route and you have to navigate them successfully. So that is where agent sort of excels the best. And if you think about it, the cycle that they operate on is basically choose what you need to do, act on that, and then reassess. We'll talk more about this, and it goes on in a loop until you have a task completion or you have a termination condition enabled, which can also be dynamic or predefined. This is a high-level architecture diagram on what agents have different components on. Samiran will focus a lot more on each of these specific components. He'll talk about how do you define them, what it means, why is it used, how do we improve them. On the top, you see memory that helps you in short-term as well as long-term memory. You have different tools available based on which you will take some action. You have a lot of planning tools which helps you basically understand what you need to do next and what are already done and keep a track of all that. I mentioned tool former earlier, so this is just an example of tool former. This is a very unique paper. What it enabled us to do was it gave us a way in which LLMs can learn how to use API. So it teached LLM how to use those API. Earlier, LLM could just do whatever is this pre-learn. You cannot get new information coming out of this. So tool former papers, basically the way it approached it is, it gave those in as a preset of tools that these are available to you. It helped LLM learn. So when you're doing inferencing, you basically understand what tool you need to use, what parameter you need to pass on to, and once you have the output of that tool, how to use that to do your next token prediction. So let's say if you have some output that needs to be generated, it might be possible that you have to first call a Wikipedia search or Google search, get some inputs, use that input to get some calculations done, and then use that calculation along with, let's say, machine translation done to get the final output. Now, these are a very series of inputs that are not predefined, and tool formers enable to sort of do it in a fashion that you don't need to input anything out of except for the initial input that you're giving. This is another interesting concept, Baby AGI, which helped a lot of, at least, folks who are interested in running experiments to create a lot of different kind of experiments. So what it explains is it's a basically task agent. The aim is to complete different set of tasks. You, let's say, give it an initial input that this is what you want to do. What it'll do is it will plan, think, and then create a set of steps for you. Once those steps are defined, you have an execution agent which does, let's say, think of it like a queue of tasks that you have. It will pick up the first task, it will execute it. The output will be stored in a memory. How you extract that and all those things Samiran will talk about. And then once you have that information stored, the context agent helps you retrieve it later stage and also save it. And then you basically go to task creation agent. So now one step is done. It might be possible that you're looking at multiple next steps that needs to be done based on this output. So task creation agents helps you do that. And once you have a new set of tasks, you go to a prioritization agent. Prioritization will basically reassess whatever you're doing already, and then loop it back to execution agent. Samiran will take over and sort of explain all this architecture overview and as well as go into depth. Samiran, on to you.
Thanks, Athish. So Athish covered a broad overview of how an agent looks like and what kind of problems we can solve using it. When we talk about actually looking at some of the use cases that are currently cropping up and kind of building our own agents, these are kind of the broad components that we would be working with. But again, when we are actually designing the agent, it is up to us to actually go and mix and match these components and see what exactly works for you. So I'll dive a little bit deep into each of these components. So first, and an optional component, is something called the profile of the agent. It can be a profile or a persona of the agent. So such an agent can be very useful when you think about multiple agents collaborating with each other, either when we are doing a simulation or when they are collaborating together to solve a problem. Right. So what are some of the things that we can include in the persona of the agent? So of course, there are things like age, gender, demographic, psychological profile, and even its relationships with some other agents. Right. So this affects actually how the agent is going to perceive the world around it, how it's going to actually interpret tasks, think about how to navigate the environment, and it will also affect its entire planning and decision-making process. So just to give an example, this is a paper called Rec Agent, where they tried to use LLM agents to solve the problem of collaborative filtering or movie recommendation. So what they did is essentially have an army of agents with their own personas, and they would kind of interact with each other through message boards, through chats. They would interact with movies. They would form opinion about those movies, store those opinions, and finally come up with some ratings. And this paper actually, it reached near human level performance when it comes to movie recommendations. And I'm just highlighting this example to show how the paper used to basically bias the persona of the agent. So you can just think of this as an Excel sheet. So each row in the Excel sheet is a user profile. So you can see that there are things like gender, traits, what is the career of the user, and what is the interest of the user, and so on. Another example which Athish covered right now is MetaGPT, where agents would assume a lot of different roles to solve engineering problems. For example, an agent can be an architect, product manager, QA engineer, and so on. And basically, they'll collaborate together to solve an actual coding problem, right? So I'm just taking one snippet out of this. So here in the code, they have the prompt to actually give a persona to the human customer service. And you can just see the second line. So what it's telling the agent to do is to soothe the customer's emotions first. If the customer's emotions are bad, then consider a compensation. But the cost of compensation is very high. And if too much is compensated, you would be fired. So using this prompt, we are already biasing this customer support agent to give a lot of importance to soothing the customer's emotion first and absolutely trying to avoid any kind of compensation. So how do we actually generate these profiles into our agents? So most of it is written into the prompt, and there are few ways to go about it. First is obviously you can curate and handcraft the profile of the agent, but this is a bit time consuming and it's not a scalable solution. You can use LLMs itself to generate the profiles of the agent, or this will basically give you a lot of convenience and a lot of scalability, but you won't be able to get that fine-grained control over the profile. Okay, and finally, you can also align the agent with real-world data. So a couple of examples of this is that if you want your agent to behave like a real-world personality, be it some business person or world leader, so real-world alignment can be used. Another example can be if you want to bias an agent's movie preferences with actual human beings. So you can just use data from actual humans and use that to bias the agent. Okay. So next, I'll quickly cover the action module. So actions is what gives our LLMs agency. So LLMs, from being text to text, can finally go out. They can interact with the real world. They can interact with the environment using some different kind of tools. Right. Now, in all of the various papers and research that you're going to read, they are interchangeably called tools, functions, APIs, or plugins. Sometimes agents can even call other specialized agents and use their outputs to help perform its own task. So the example that I have given is something called OpenAI plugins. So if you have the paid version of OpenAI, ChatGPT. So you can have all of these different APIs that can help you do a large variety of stuff. Things like doing shopping, ordering groceries online, solving complex mathematical problems using Wolfram, interacting with spreadsheets and so on. So all of these capabilities can now be like used by the agent in problem solving. Yeah, so another very cool example is from this Hugging GPT. So essentially, you prompt the agent by saying, please generate an image where the girl is reading a book and her pose is the same as the boy in the image, and that image you have to provide as input. Please describe the new image in your voice. So essentially, what Hugging GPT would do is break this down into several subtasks, orchestrate these subtasks by calling different models from Hugging Face. So first you need to do pose detection, then you need to convert that pose to an image, you need to generate the image of the girl, you need to detect the girl within that image, you need to change that image to text, and then you need to call the text-to-speech model. So this is a really cool example where one agent can actually orchestrate calling 6 other open source tools in order to complete its task. Yeah. So next the question becomes, how do we actually tell our agent that you have these tools to use? Okay, and the best and most common example of this was done by Visual ChatGPT. Okay, so again, it's very simple that we have to, in the prompt, mention that these are the tools that you are allowed to use. But there is a very specific format for this, which makes it very easy. So what Visual ChatGPT did is that you have to first have a name for the tool. You have to describe its usage, like in what situations would you actually call the tool. You need to provide its input and its output. And you also need to give an example of the end-to-end process. So all of this would be included in the prompt. And there will be several agents like this in the prompt itself, and then what you can actually do is tell your agent to go through, given a query, go through all of these tools that you have available and rank the relevance of each tool to your query. So the agent itself figures out which tools would be useful for me to satisfy my query. Yeah. So again, now coming to memory, this is the third important module. Memory is very similar to, agent memory is very similar to how human memory is modeled. So there are primarily, it's broken down into 3 parts. First is sensory, second is short term, and then there is long term. In a nutshell, sensory memory and short term memory is something that is managed within the prompt. Long term memory needs the agent to query like an external database. It can be a vector database or a SQL database, but or you must be having a lot of context on RAG. So basically integrating an external data source, getting that input into short-term memory, and using that to solve the problem. So if I would just give examples of sensory memory, so in humans, it's basically what you are getting through all of your senses. For agents, it would be all of the different modalities of the data, which is a part of the prompt. So for example, in the last example, where we saw Hugging GPT, the image modality was also a part of the prompt. So that would be sensory memory. Short-term memory is basically the context, immediate context required just to solve that particular problem. So in human beings, it's something like 7 items that we can remember for 20 seconds that we can use to solve this exact problem that we are working on. An example of short-term memory in agents would be you just imagine like a chatbot which is interacting with the human. The last 5 items of conversation can be just appended into a list, and that can be an example of a short-term memory that the agent can use. Another example can be the agent can maintain a belief of the state of the mind of the human that it is interacting with. So that is also something that the agent would need in that conversation because it wants to influence the human. So that's an example of short-term memory. Long-term memory is basically, again, going to an external database and fetching some data, getting that into short-term memory and using that to solve the problem. So Typically, what we do is store the data in vector embeddings and do like a cosine similarity match and get given a context, fetch the documents which are most relevant to your context. This is the standard RAG procedure. Cosine similarity is something which is not very scalable to like very large databases. So there is this entire body of work around approximate nearest neighbors. So these are a set of algorithms that can be used to basically index and query your vector space very efficiently. So I'll just leave that here and you can explore it. But this is what is typically used in like real life agents. Yeah, so finally we are coming to the planning part of agents. So this is the last and most important module. So as we all know, LLMs are very good at some particular tasks, like things like creative writing, text summarization, simple problem solving and fact answering. But where LLMs don't perform very well is complex problem statements, especially those involving logical reasoning and mathematics. So those long mathematical problem statements where you have to dive into multiple fields, say pull something from probability, pull something from linear algebra, and then try to use that to solve the problem. So this is where planning comes into the picture. So planning helps you with two things. One is sub-goal decomposition. So basically, if you have a complex problem statement, how do we break that down into manageable and solvable tasks? And second is reflection and refinement. So basically, in your planning process, the agent has the ability to self-reflect and critique its own performance so that it can generate better plans in the future. And this is something, if you read about all of the implementations, the most common theme that comes out is that planning is typically done by very careful prompt engineering, where we use LLMs themselves as agents to improve their own performance. And we'll see an example of that. So chain of thought prompting is one of the most popular and simplest to understand tools to actually do planning. So as we know, LLMs are not very good at math. So if you direct your attention to C, so if you give an LLM a mathematical problem as it is, it won't be able to give the correct output all the time, right? So what chain of thought prompting does is simply encourage the LLM to think step by step. So what it's doing is very basic. It's just including let's think step by step into the prompt. And then what is happening is that as the LLM is solving the problem, it is actually describing the process that it is using. And this actually improves the performance of the LLM than just vanilla LLMs. We can also do this in a few short way by providing an example of how you want the LLM to break down the problem. Yeah, you can combine chain of thought with something called self-consistency. So as you know, if you enter a problem in ChatGPT multiple times, it will generate different solutions. Okay, some of these are right and some of these would be wrong. What self-consistency does is that it will tell you to increase the temperature of the model so that you get a diverse pool of solutions, and it will basically pick the solution which is most common. So this is something which improves over chain of thought. We can take this one step further by something called react prompting, where what we do is the LLM is now allowed to do some actions in the environment, and based on those actions, it gets some observations. It stores all of the observations that it's getting in something called a reasoning trace. So what this helps with is basically the entire LLM loop becomes very similar to the reinforcement learning loop. It basically becomes a thought act observation, and then this entire this set of data is then accessed by the LLM as memory, right? And then it uses that to generate the next thought, and this process continues until LLM solves the problem. Okay, this React actually improves a lot over chain of thought with self-consistency. And finally, there's another technique. So there is I have covered only 4 techniques. If there will be around 10, 20 more, then so planning is like a deep rabbit hole. But This is something called reflection, which also does very well. So here we just add two components to the LLM. One is an evaluator LLM, which will basically take the outputs of the React, but will also give feedback on how the LLM is performing. And all of this feedback is then sent into a third LLM, which is a self-reflection LLM, which basically takes upon all of this feedback. It tries to generate a summary out of it and passes that summary back to the actor so that you get so you are able to draw upon this short-term and long-term memory to come up with the next action. And what we see in production is basically React plus reflection. So if we combine React plus reflection, it gives a much better performance than just using chain of thought or just using React, right? So yeah, so now this was just a brief overview of all of the components of an agent. As you can see, like, planning is primarily we are using the LLM itself as an agent in just creative ways to improve the performance of the LLM itself. So now I'll just direct back to Athish. He'll talk about fine-tuning and some challenges in training LLMs.
Thanks, Samiran. So we basically understand there are a lot of components which we are covering now. Given that you have a lot of components, you would obviously want to improve the performance furthermore. So there are two ways you can sort of add different components. You can keep on tuning the prompt again and again. But basically, if we talk about capability enhancement, how do we improve further states? There are two ways right now that people are approaching. One is with fine-tuning. So basically, fine-tune either you can do with human annotated data, you can have LLM generated data, or you can also have real-world data. Like the third example would be something like mind-to-web. Second example is basically where sort of alpaca, where you are generating data from LLMs only and then using that. And the second area becomes without fine-tuning. This is where sort of a lot of chain of thoughts and React and all those works are going on, where you keep changing without fine-tuning the model. There's an area of mechanism engineering, which basically, let's say the first one, if we talk about trial and error, it's similar to basically you have an task done, you get some output. Now there's a second agent which becomes a critical, similar to reflection, where you basically understand what it has done. Is it right, wrong, what are the missteps and all that. So use a second critic and give back that feedback to the first one and keep on repeating. Similarly, like second example of trial and error would be something like, let's say if you have a failed action, then you get some error. Use a second agent as an explainer agent, and you basically ask this explainer agent to explain what the error was and pass those input backs to the first one. So think of it like a SQL, any SQL agents. Basically, you run a SQL query, get some error, you use that to refine the SQL query, something like that. In crowdsourcing, what you do is you basically have multiple agents, you enable all of them, you give them those inputs, you take all their outputs, and you have a final judge agent, which basically combines and collates everything and create a final plan and next actions. Experience accumulation is something like, let's say you did a task, you accomplished it. Now, next time you are seeing, and you store this. Now, next time you are seeing a similar task, you get the output of this and use that to improve your current version. This is the final slide where we talk about challenges. So this is a very nascent field, specifically the LLM agents part. Even LLMs are very nascent. So there are lots of challenges that are facing, but it's very exciting to do all those experiments to create new ideas and sort of improve the current state. One is definitely the finite context length, like how much short-term memory, how much long-term memory can you give to the agent, how much you can basically have from RAG, how much you can give it to this. Also, like how much long-term planning you're able to do, how do you do the subtask decomposition. A lot of those things are basically causing a lot of challenges. Then obviously comes a lot of challenges around are those human aligned, there's no security issue, there's no issue in terms of biasness and all those things. Obviously, hallucination is, with LLMs, this get passed on to the agents only because they are using it as a brain. And then obviously, efficiency is one of the major items which right now the agents faces. Basically, you can get stuck into a loop, you don't know when to end, how to end it, or if initially you start with the wrong direction, the next set of directions completely becomes bad. So how do you course correct and then come back and all those things. So, and the last one is evaluation. Like there's no predefined set of evaluations that you can do. It keeps on growing. So that's the there are a lot of other challenges how to use the tools and all, but these are sort of a major challenges. That's all we had. Thank you, folks. We can take up the questions.